Welcome back to the deep dive. Today we're going to do something a little different. I want you to imagine taking that old biology textbook you have, from high school,
Oh.
and just putting it in a shredder.
And then launching the shredder into the sun.
Exactly. Because the stack of research we're covering today, it completely dismantles the standard definition of life.
Oh, it really does.
Yeah.
Usually when we talk about biology or even, the search for extraterrestrial life, we have this very comforting checklist.
Right.
Life needs carbon. It needs liquid water. And it absolutely needs a Goldilocks zone.
That perfect orbital distance, not too hot, not too cold.
Precisely. We think of life as this fragile thing that needs a very specific environment.
A blanket, basically. But the papers you've pulled for this episode, they just throw that blanket right out the airlock.
They really do.
We are looking at organisms that don't just survive in the worst places imaginable. They treat them like a spa day.
We were talking about life thriving inside the corona of a star.
And on the flip side, others that eat radiation in the absolute frozen vacuum of deep space.
It's the xenobiology of the void. And specifically, we're doing a deep dive into two species that honestly shouldn't exist by the book. Reticulum stellaris
The photonic lattice.
and a Solsilva radiovora.
The astrophage. So one lives on the sun, and the other one pretends to be a rock in the dark.
That is the back of the napkin version, yes.
So our mission today is to unpack the how, because the sources claim these things swap out carbon for silicon, they swap water for ionic liquids, and they swap food for raw nuclear energy.
Yeah.
I want to understand the mechanics. How do you skip breakfast and just eat a gamma ray instead?
To get there, you have to rethink biochemistry from the ground up, from the atomic level. You
Okay.
need to stop thinking in terms of flesh and blood and start thinking in terms of lattice and current.
All right, let's start with the hot one then. The sun dweller. Reticulum stellaris. When I first read that name in the source material, I was picturing, some kind of fire elemental, a plasma blob.
Yeah, that's what everyone thinks. But it's not a blob at all. The morphology is so much more precise,
Oh,
almost industrial.
industrial.
If you were close enough to actually see it
Yeah.
and somehow survive millions of degrees, it wouldn't look like an animal. It would look like a shimmering, crystalline membrane.
A membrane.
It's a colonial superorganism.
Okay, let's unpack that. Colonial superorganism. So a lot of little things acting as one big thing.
Exactly. The basic unit of this creature is the monomer.
Okay.
Imagine a microscopic hexagonal flake, only about 50 microns wide. On its own, it's just a speck of silicon graphene.
But biologically,
It's a solar sail.
a tiny solar sail. And I'm guessing they don't stay alone for long.
No, they can't. To survive just the chaos of a star's atmosphere, they have to lock together.
Wow.
They use electromagnetic adhesion to link up,
Yeah.
millions upon millions of them, and they form these vast shimmering sheets. The sources describe them as mirrors that can be thousands of kilometers wide,
Thousands of kilometers.
just drifting through the corona.
That is a terrifying scale. A
Yeah.
living sheet the size of a continent floating on the sun. But this is where my brain starts to break. The heat.
Yeah.
Logic says if you touch the sun, you burn. You vaporize. How does a biological sheet not just instantly turn to ash?
That is the primary evolutionary hurdle they had to clear. It all comes down to albedo management.
Albedo. So reflectivity.
Exactly. The dorsal side of this sheet, the side that's facing the star, has an albedo of nearly 0.99.
0.99. So it reflects 99% of the light hitting it.
It's a near-perfect mirror. It reflects almost all that thermal and light energy away. It just refuses to accept the heat.
You can't reflect everything. Thermodynamics is pretty strict about that.
Right, some heat always gets in. It's unavoidable.
So they have to cool down somehow.
They do.
Hmm.
The ventral side, the side facing away from the star toward empty space, acts as a radiator.
Ah, okay.
It uses the Stefan Boltzmann law to dump waste heat as efficiently as possible into the vacuum. So it's a mirror shield on one side and a radiator on the other.
It's an engineered solution, but it evolved naturally.
Yeah.
That's incredible. So it's surviving, but it's not just floating there. It has to be eating.
And you said there are no sandwiches in the corona.
No sandwiches. And this is where we really leave standard biology behind. Plants on Earth use photosynthesis, right?
Yep, turns sunlight into sugar.
This organism uses something the sources call Dyson synthesis. And its engine is nuclear isomerization.
Okay, nuclear isomerization. That sounds like something you need a security clearance to even talk about. Break that down for us.
It's actually based on some pretty high-level physics, but the concept is, well, it's wild. The organism's cells are transparent to specific high-energy wavelengths.
Like gamma rays and X-rays.
Exactly. And inside the cell, there's a core that is doped with the element hafnium.
Hafnium. Okay, I know that one. It's a heavy metal. We use it in nuclear control rods.
That's the one. And hafnium has this very unique nuclear property. When a high-energy photon like a gamma ray hits a hafnium nucleus, it doesn't just heat it up.
What does it do? It excites the entire atomic nucleus into a metastable state.
A metastable state, meaning it holds the energy.
Think of the nucleus like a spring. The gamma ray hits it and coils that spring incredibly tight. The energy isn't stored in a chemical bond, like in sugar. It's stored in the atom itself.
So it's a living nuclear battery.
Precisely. And the energy density is just.
Yeah.
It's millions of times higher than chemical explosives. It's an insane amount of power.
Which you would need, I guess, if you're trying to move against a star's gravity.
You absolutely would.
Yeah.
Which brings us to locomotion.
Right. It doesn't have rockets. It doesn't have wings. The wings wouldn't work in a near vacuum anyway. How does a giant sheet move around the sun?
It balances two fundamental forces: radiation pressure and gravity. It's a surfer.
A literal solar surfer.
Think about it. The sun is constantly blasting out photons. That stream of light creates pressure, a real physical push.
Okay.
When Reticulum stellaris wants to ascend, to move away from the star, it flattens out its whole lattice. It maximizes its surface area to catch the light,
And that pressure pushes it outward.
overcoming the star's gravity.
Yeah.
So how does it go down?
It tilts edge on, like feathering an oar or turning a sail into the wind. Suddenly, there's almost no surface area for the light to hit, so the radiation pressure drops to near zero.
And gravity takes over, pulling it back down.
Pulls it deeper into the corona to feed.
The source is also mentioned it uses magnetic fields for steering.
Yes, for lateral movement. They use Lorentz forces.
Okay.
They can induce electrical currents within their own lattice structure. And because they're swimming in the sun's powerful magnetic field, running that current creates a physical force.
So they can push against the magnetic field lines.
They can grab onto them. They ride them like rails.
Surfing on light and riding magnetic rails, that is just unbelievably cool. But there's a flaw in this design. A big one.
There is.
The sun has infinite energy, sure. It's an all-you-can-eat photon buffet. But the sun is mostly hydrogen and helium.
Correct.
And this thing is made of silicon and carbon and hafnium. You know, heavy stuff. You can't build a baby solar sail out of hydrogen gas. And you've just hit on the central conflict of their entire existence. The star is a gas station, but it's not a hardware store.
They have infinite horsepower, but no parts for reproduction.
Exactly. A single monomer could, in theory, live forever in the corona, repairing itself. But it can never, ever replicate.
So they have to commute, the cometary migration.
This is a complex four-stage cycle, and it's one of the most, frankly, violent biological processes I've ever read about.
Okay, walk us through it.
First, you have the charge phase. The colony just hovers in the upper atmosphere, soaking up all the gamma rays it can, charging those hafnium batteries to 100%.
And then the launch.
The transit. They use a massive coordinated burst of that stored nuclear energy to generate laser ablation thrust.
Wait, laser ablation, that means they burn part of themselves to move?
Yes. They vaporize a portion of their own ventral mass. They create a jet of high-velocity plasma.
So they literally turn themselves into a rocket by burning their own body.
They become a torch ship. And they blast themselves out of solar orbit and head for the nearest rocky body. An asteroid, a planet, whatever's close.
And when they land on this asteroid,
they disassemble. The giant sheet breaks apart into those billions of microscopic monomers. The source describes it as a gray goo phase.
that sounds ominous.
It is. They coat the asteroid and begin to chemically etch the rock, pulling out the silicon, carbon, and hafnium they need.
Using that stored nuclear energy to power the whole process.
Right. And they replicate exponentially.
So they turn the asteroid into a nursery, they eat the rock, build millions of copies of themselves, and then what?
The return. Once they've doubled or tripled their numbers, they link back up. They form a new, even more massive sail, and they ride the solar wind all the way back home to the star.
And start the cycle all over again. It's terrifyingly efficient.
It is.
But this also gives us a clue on how to find them, right? I mean, we can't exactly see a mirror against the sun.
It's very difficult, but there are telltale signs in the data if you know what to look for. The first is what the paper calls the hafnium gap.
Hafnium gap.
Because they absorb very specific frequencies of gamma and X-rays to charge their cores, An infested star will show these artificial absorption lines in its high-energy spectrum.
So it would look like someone took a bite out of the rainbow, but in the X-ray band.
That's a great way to put it. And if the swarm gets big enough,
You'd see shadows.
coronal shadows,
Yeah.
they'd physically block telemetry, or they'd cause the star's light to flicker in these very non-random patterns.
So if a star is flickering and missing some of its X-rays, it might have a parasite.
Or a very shiny, very crowded ecosystem.
Okay, let's pivot now. We're leaving the inferno. We're going to the absolute opposite end of the spectrum, the deep, dark void.
Right.
Let's talk about the Astrasilva radiovora.
Yeah.
It's astrophage.
Star forest radiation eater.
Yeah.
A very poetic name for something that, frankly, looks like a space potato.
It really does. The camouflage is perfect. The source says it looks exactly like an asteroid or a comet.
That's its primary defense mechanism. Its exoskeleton is biomineralized. It's made of silicates and iron-nickel alloys.
So to a radar scan or a predator?
It just reads as rock and metal. Nothing to see here.
But inside, it's alive.
Very much so. Inside that shell is a complex photochemical core that acts like a reactor. It practices radiotrophy.
Which we actually have on Earth, right? This isn't completely out of left field.
We do have a precedent, yeah. There are fungi found growing inside the ruins of the Chernobyl reactor.
Right. They use melanin to feed on ionizing radiation.
The astrophage does the same thing, but on a cosmic scale. It captures cosmic rays, background gamma radiation, but it has another trick up its sleeve. Something Earth fungi definitely don't have. It uses a hydrogen fusion analog.
Whoa. Fusion inside an organism. Fusion needs the gravity of a star to crush atoms together. How does a rock the size of a car do fusion?
It cheats. It uses quantum tunneling.
Okay, that sounds like a magic spell. How does that work in biology?
Imagine you have a ball, and you want to roll it over a really steep hill. In classical physics, if you don't push it hard enough, it just rolls back down.
Right. The hill is the energy barrier.
And fusion is getting the ball over that hill. The astrophage doesn't have nearly enough energy to push the atoms together that hard.
So it should fail.
In our world, yes. But in quantum mechanics, there's a tiny, tiny probability that the ball simply passes through the hill, like a ghost.
It tunnels through.
Exactly. And the astrophage has evolved biological structures that align hydrogen isotopes so perfectly that the probability of them tunneling through that electrical repulsion barrier skyrockets.
It forces the atoms to walk through walls.
Effectively, yes. It's biological cold fusion. It's not a high-output burn like a star. It's more of a slow, smoldering warmth.
But it's enough.
It's enough to keep its internal fluids liquid during the long, cold drifts between solar systems.
And it moves, too. I
Yeah.
mean, not fast, but it moves.
It uses ion propulsion. It has these tiny electromagnetic nozzles in its exoskeleton. It expels charged particles to create a very weak but incredibly efficient thrust.
Like the ion engines NASA uses on deep space probes.
Exactly the same principle. Slow and steady wins the race when the race is 1,000,000 years long. They also use gravity assists. They calculate these complex trajectories to slingshot around planets and gain speed without spending any energy.
Now, what blew my mind was the scale of these things. They aren't all just rock-sized. They grow.
Oh yeah, they have distinct life stages. The juvenile's about the size of a bowling ball, maybe 30, 40 centimeters. At that stage, they're scavengers, really mobile, darting around planetary rings.
Then they mature.
The mature stage is the size of a car, maybe a bus,
Yeah.
3 to 5 meters wide, weighing up to 3,000 kilograms.
Yeah.
This is where they settle into that long-haul traveler lifestyle.
But then there's the giant variant.
The boulder.
Yeah.
10 meters plus,
Yeah.
20,000 kilograms. And at that point, they're not just organisms anymore. The source calls them mobile ecosystems. They're these massive biological tanks drifting through the void, likely hosting smaller symbionts or even parasites inside their shells.
How do you even make more of yourself when you're a living rock floating in total emptiness?
You use a process called biological terraforming. They release these dormant spores that are encased in incredibly tough ceramic-like shells.
And the spores just drift.
They drift until they hit a comet or an asteroid. Then they activate.
So the spore lands and it just starts eating the asteroid.
It eats the rock to build a new body out of it. It's a slow process, might take decades just to hollow out a landing site and build a shell. But time means nothing to the astrophage.
Then they can hibernate.
They can enter dormancy. The notes mention thermal equilibrium.
Right.
They can shut down their metabolism completely,
Yeah.
let their body temperature drop to match the background temperature of the entire universe, 2.7 Kelvin.
That's basically absolute zero.
It makes them completely invisible to thermal sensors. They can just sleep for millions of years drifting, waiting for a gravity well to pull them in.
It really makes you wonder about the evolutionary history here. I mean, how does nature even come up with something like this? It feels like we're looking at two totally different branches of a very, very weird tree.
The evolutionary paths are just fascinating because they show how life adapts to whatever energy is available. Let's look at the photonic lattice first. The sources suggest it started on a hot Jupiter.
A gas giant orbiting super close to its star.
Right. The era called the Lithic Dawn. 3.5 billion years ago, they didn't start as life. They started as piezoelectric crystals forming in magma, just non-living geometric structures that grew by organizing silicon.
So they were basically crystals that got zapped by lightning.
Essentially, yeah. Electricity organized them. Then, as the planet's environment changed, they moved up. The photonic shift. They became atmospheric plankton riding thermal updrafts in the clouds.
And then the planet lost its atmosphere.
The great filtering. The star's heat just boiled it away. The only ones that survived were the ones that could seal themselves against a vacuum. And then came the orbital jump.
The moment they became shiny.
The moment they became mirrors.
Yeah.
They realized, biologically speaking, that light could push them. They didn't need wind anymore.
So they just left.
They spiraled inward, abandoned the dead planet, and colonized the star itself.
That is an epic journey. From magma to clouds to the sun. What about our rock friends, the Asteroids?
Their story begins much earlier, in protoplanetary disks. The swirling dust and gas around young stars, before planets even form.
So they were literally born in the dust.
They started as prebiotic compounds on ice grains. Over millions of years, they built shells to protect themselves from collisions in the disk. And they just stayed there.
While the lattice chased the light, the astrophage mastered the dark.
And if you look at their biochemistry, the contrast is just so stark.
Well, let's compare them.
Well, both of them reject water. Water is useless in these extremes. It boils on the sun, it freezes solid in the void.
So what do they use?
The photonic lattice is a graphene-silicon hybrid. It's built for heat and tension. The astrophage uses ionic liquids.
Like liquid salts.
Exactly. Solvents that act like water, but they won't freeze in deep space or evaporate in a vacuum. And their genetics, totally different from ours. They use sci-DNA.
Silicon-based DNA.
With a boron backbone.
Boron. Why boron?
Stability. Carbon DNA. The stuff we're made of, it just unravels under high heat. It breaks down under heavy cosmic radiation. It's too flimsy for the void. Silicon and boron are tough. They're built to last for billions of years.
So what does this all mean? We've got solar sails made of graphene and living asteroids running on ion drives.
It means we really need to stop looking for Earth 2.0 when we hunt for life. We are obsessed with finding oxygen atmospheres and blue oceans.
But these organisms, they turn the so-called dead zones of the universe into thriving ecosystems.
We look at a star and we think, nuclear fire, nothing can live there. The lattice treats it like a gas station.
And we look at the void between stars and think, empty, cold, dead.
The astrophage treats it like a feeding ground.
This fundamentally challenges the entire search for extraterrestrial life. We're out there looking for biosignatures that match us.
And we might be completely missing the hafnium gaps. We might be ignoring asteroids that move just a little bit differently than physics predicts.
That's the scary part for me, the camouflage. If an astrophage is dormant, it's just another rock. We could have one sitting in a museum right now, classified as a meteorite, and we wouldn't know it.
Not until it decided to wake up.
Right.
But consider the implication of the photonic lattice migration. We talked about how they strip mine asteroids to reproduce.
Yeah, the gray goo phase where they just eat the rock.
Okay, so imagine you're an astronomer. You're observing a distant star system, and you see a dense asteroid belt. Then over a few centuries, that belt just starts to thin out. Rocks just vanish.
Because they're being eaten.
And converted into new solar sails. Now, if a swarm only leaves its star when it overpopulates, a sudden disappearance of an entire asteroid belt could be the very first warning sign.
A warning sign of what?
That a stellar infestation is about to expand outward.
That is a haunting thought. We worry about invasion fleets with ships and lasers. Maybe we should be worried about a swarm of mirrors looking for fresh rocks.
It really changes the way you look at the night sky, doesn't it?
Yeah.
It's not just stars and rocks anymore. It's potential hosts and dormant travelers.
It certainly does. So next time you're stargazing, take a second look at those empty spaces and maybe keep an eye on the sun, just in case it flickers.
And remember, life finds a way, even where we think it's impossible.
Thanks for diving out with us. Keep looking up.